Today we're going to be talking about simulating a process of hydraulic fracturing to extract natural gas, and it's really just the water portion of that process. I borrowed the basic concepts from a spreadsheet, and let me show you where that came from. By the way, if you're having any trouble viewing or hearing me, viewing the screen or hearing me, please let me know during this presentation. Looks like we're okay so far. Okay, so here's the spreadsheet file, and it was obtained from a publication online that's actually it's an interesting one called Environmental Life Cycle Analysis of Water and CO2 based fracturing fluids used in unconventional gas production. So now this is definitely much further above and beyond what I'm doing in this presentation, but it could certainly be evaluated starting with the model that I've built so far. What it does is the spreadsheet, it looks at doing a hydraulic fracturing using a water-based fluid and then another with CO2, apparently. So, and then it just compares the emissions from both of those, and it looks at all kinds of things like the energy requirements, for pumping and diesel use for trucking and all of that stuff. So it looks at a lot more than just water. But one thing that I'd like to make note of is that, and you've probably run into this before using GoldSim, when you look at converting an existing spreadsheet over to GoldSim, obviously it's not a good idea to just blindly just start walking through all of the cells one by one and just replicating the descriptions and the values and then go down to the expressions, right, and just start typing them all in. I mean, it would be probably pretty straightforward to replicate exactly what was done in Excel in GoldSim. The problem is, what you start running into is, first of all, there's not a lot of use if you're just doing exactly the same thing. But also, since GoldSim is a dynamic simulator, you'd probably want to be looking at, the system changing through time, and that's not what this particular spreadsheet's doing. But also, you want to, make sure that you understand the basic process that's going on. Otherwise, as soon as you try to deviate from what's going on in the spreadsheet, it would become very difficult, obviously. And I will admit that it was tempting for me to just do what I said not to, which is just start typing in all the expressions. But the other thing that happens is GoldSim is very explicit about units, and so you have to be very careful. For example, in the model here where it said, it gives a value for something like, let me just say, for example, total volume of fluid per stage of the well lateral that is injected for fracturing is this volume. Well, that's just one number. It takes a while to get that volume down into the ground, right? Over time it goes down. So if we're doing a simulation, a dynamic simulation, then you may want to consider this as a flow rate. So then you're dealing with units, and there might be repercussions of that, in other expressions that and other complexities that are not included in the spreadsheet. So that's precisely what happened to me. And so, like I said, the model that I developed is really just for looking at water. This spreadsheet has a lot more, and you could go forward with what I've done if you want to, or just use the spreadsheet. But anyway, I will provide this file along with the model file, the GoldSim model file, which includes the documentation here, if you want to see where this came from, and look at all that. So let me go back to the GoldSim model, and just kind of walk through it. Now, this is actually a work in progress a little bit. There are a few loose ends here, and I thought it would be a good opportunity to walk through. It's kind of like a real world situation here where we need to document a little bit, clean up a model, and I'll show you some ways that I'll be doing that, and also walk through the process of looking at how I'm simulating the well lateral. Okay, so let me back up a little bit and just talk briefly about hydraulic fracturing, and I apologize to those that are professionals in this arena, because I am not. I'm a water resources engineer, and I have read up on this topic, but I am not an experienced professional in this specific field. So if you are, feel free to interject as I'm going along here and correct me where I might have made a mistake. But in essence, what's happening here is a well is drilled down vertically into the ground until we get to a shale strata where the gas is, and then there's a bend, and then the well is continued to drill horizontally through that layer. And once that's done, then there's a process of going through and perforating it in sections, and then pumping water mixed with chemicals and something called propellant, which is potentially, maybe it's sand, maybe it's some other things, little balls or something, that goes down in there, and it opens up it keeps the cracks open. Once you pump the fluid down there at a high pressure, the shale cracks, opens up these little fractures, and then the little pieces of sand or other whatever the material is goes into those little cracks and keeps them open, and that's how the gas comes out of those cracks. As soon as you stop exerting the pressure down in there with your fluid, then the fluid comes back out along with the gas. But this is done in stages typically. So what that means is you first go down and you perforate just the very end section where I'm pointing down here. Let's say the very end of this horizontal lateral. Let's say you just perforate the last 1/10 of that lateral, and then you pump the fluid in there, and once that's done, it fractures, and then you plug it, and then you go to the next section and repeat the process of perforating and then fracturing and then plugging, and you keep going all the way back until the whole lateral is complete, and then you drill through those plugs again and allow the gases and fluid to come out. So it's kind of this staging process that in which you're pumping fluid into each of the stages, and then whatever is left after, any losses, where you might have some losses that occur, obviously, right? So fluid that's pumped into these fractures could be lost into the surrounding ground. So you need some losses, and then you need to be able to simulate the process of the flow coming back out. Okay, so that's what is done essentially in this page of the GoldSim model. But if I browse all the way back up to the top of the model, I have some graphics in here that probably need to be taken out. I was just adding some stuff in here to kind of get a feel for what's going on. But essentially, the whole system includes some water source, and my water source is just a generic river here. And actually, I was using a pool. I decided to use a river as a water source, and the reason for that is because it could be limited, and you could show that, well, maybe you need some environmental bypass flows in the river, and that would be a more interesting view of what might be available on your source end. So I run the model, and this is just random numbers, but let's say this is your river flow here. From that point, then we can deliver water into the system. Okay, so that's our source. It comes into some impoundment, let's say just a pool of water using maybe embankments that have been built. And from there, then we pump water into trucks, mix chemicals with it, and the chemicals and the sand with the water, goes into these trucks. Trucks drive over to the wellhead, and then the fluid is then injected into the well, and then we have flowback, and so that's what's coming back out with the gas. So we have gas produced. We have a little bit of wastewater, but then we can recycle. That's this stream right here. The recycle can come back into the impoundment, and we start the process again. Okay, so that's kind of how it's working. However, it should be noted that this water system is demand driven. So what we have, and what I found from the Excel file, is I'm using some numbers from this. So for example, there's a number here that says how much, let's see, where was that? 72. So yeah, the other thing about spreadsheets is it's really kind of hard to look at your expressions, right? Because you're dealing with cell numbers. So you have to constantly be looking at things like this. Okay, so I'm using the same total volume per wellhead right here, this 90,000 cubic meters. And there are a number of laterals that can be within the wellhead. And within the lateral, then you have stages. So in this case, it says there are 10 stages within one lateral. And then you could have multiple laterals per wellhead. And then you could have multiple wellheads. So what I'm doing is I'm simulating just a single lateral in this model. Somebody said the color in the spreadsheet, yellow and green, are that you made. I don't think so. No, I don't think I did any coloring in this spreadsheet. So no, the answer is no. I think that was already like that. But when you go to this, when you open this document and you click on this link here, you can see that there's a supporting info link on there. Just click on that and you can download the same file, and then you can see how it's all color coded. I don't remember color coding any of these myself. Okay, so that brings you back to the well injection. Okay, so I'm just simulating a single lateral. It would be pretty easy to just replicate what I've done for a single lateral and duplicate that for the others. You might ask, well, why not just use the same equations for multiple laterals? Well, the problem is that we're waiting. It takes time for these to flow back, for the flowback to come back out, and so you might want to be well, let's see. I guess you wouldn't drill a second lateral until all the flowback is complete. So I guess you could. I guess you could just reuse the same functions and just put in a trigger that says, when it's drained to some threshold, then begin again, the same process, assuming it's a new lateral in here. Anyway, we come back over here to flowback. And in the flowback, we need to do a couple of things. We need to split off the amount, the percentage of the gas that's in there, and then everything comes back over to the impoundment. I'm assuming that we just keep whatever chemicals came in there, also came back from, any chemicals produced from whatever came back from the fractures would also be in there, and it comes back into the impoundment and then back in again. Obviously, you might want to have some treatment in here, which I don't at this time. So anyway, that's the basic water system. But let me go back into just the lateral and describe what's going on there. Okay. So in here we have essentially this thing called the wellhead capacity, and that's based on the number of stages. I have 10 stages per lateral, and that's the amount of volume. That's from the spreadsheet. That's how much water is needed per stage right there. So we need 15,000 cubic meters. Okay, so to pump that amount in, then that's based on the flow capacity, which I have here as the amount of, this is the rate at which we can pump the water down in there, 0.02 cubic meters per second. So given that, I'll come in here to the staging flows, and what we do is we say, okay, when do we start injecting water into the first stage? And the first stage is actually at the very end. So that's the very tail end of this lateral. That's stage 1. Okay, so we start injecting the water down in there. Well, when do we do that? We need something to trigger when we do it. I'm going to turn off the browser window here so you can see the whole screen. Okay, so I have a trigger over here that's called injection complete. And let me see what that says. That says, okay, when stage 10 is full, okay, so I'm just going down here at the very tail end. Actually, this is the beginning. This is the 10th stage, which is the final stage of the horizontal lateral here. As soon as that becomes full, then that's going to trigger this trigger called injection complete. And you can see when that triggers by plotting the event count, and you see that it triggered just after day 11, which means that's when the stage 10 filled up. Let's look at it. Okay, so here we are. We're starting to do the fracturing in the last stage right here, and right up at this tip right here is when we hit the capacity, and that triggers this injection flow rate to stop. Okay, so before that happens, before this stage 10 is full, we're still pumping water down into it. So the way this works is we say, and here's a plot of all of the stages at once, right? So I open this up, and what it says here is that we start pumping fluid into the first stage. Okay, that fills up, we plug it, we go to the next stage, we fill that up, we plug it. Now I did not put any delays between filling one stage and the next in sequence, which there probably would be a bit of a delay. And in my simulation settings here, it shows that I'm running this for 20 days and it's a 1 hour time step. So certainly we could put delays like that in there with a 1 hour time step. Maybe there's a few hours in there where it takes to go from one to the next. This model also assumes that everybody's working 24 hours a day. Okay, so anyway, each of these stages then fills up until we get to the very end. As soon as we get to the end, we say, okay, everything, all the fractures are all filled. Now let's go ahead and bore through all of the plugs and allow the fluid or the flowback to begin. Okay, so that's what's happening here, and this shows how all the stages are drawing down. And so you might be wondering, well, why are they all drawing down at different rates? Well, I had to limit the discharge from these stages to, there's only one end, right? There's only one way the water can come back out, and that's through this final stage 10 on this end. That's the only way the water comes out. So you can't have water flowing out of all of these. They need to flow into the next one. And it also needs to be limited to what's flowing out of the last one. So if there's a bottleneck somewhere, if there's a lot of volume sitting in stage 10, then you're not going to be able to force the water, from 9 into 10. And so what I did is, and this is just basic mass balance. There's probably you could probably put more accurate hydraulics into the control of the flows through each of these stages. But all I did is I said, in each of these stages, the outflow here going to flowback is really just dependent on whether or not there's more volume in this current stage than the next one downstream. Otherwise, it's going to have to wait until the next one downstream drains a little bit more than this one. So essentially, you just have to draw the next one in sequence down before you can get water flowing into or flowing out of this one. So let me explain this equation a bit more, but before I do that, I'll show you this flow back on, what that is. So what we talked about up here is that we have a way to control when the injection is occurring, right? So we wait until the last stage is filled up, then we trigger the injection over here to turn off. So if I go to the off trigger on my injection, it says the injection is complete. That means turn it off. When do we turn it on? Well, we do it automatically. So I'm using an auto trigger when the model activates. That means as soon as you hit go, as soon as the simulation begins, then you begin the injection. I suppose what we could do here, and I don't think this would mess the whole model up at all, like we could come in here and we could say, no, I want to wait 3 days before I trigger the beginning of the injection. So let's just try that. So at E time 3 days, let's see what that looks like. I hope it works. Okay, so it waited for 3 days before injection begins, and then the same thing occurs going forward from that point. So you could do something like that. Essentially, all this does is it just says, okay, when do you want to start the injection? That's this trigger. And when do you want to stop it? Well, we want to stop it as soon as the whole thing is filled up, right? And the whole thing's filled up when the last stage is completed. Okay, so that's the injection side. Now on the flowback side, what we need to do is we need to say, well, let's trigger the beginning of the flowback. So triggering the flowback here is based on when stage 10 is full. As soon as that fills up, okay, we can begin flowback there. So if I go here to flowback on, it says, when do we trigger this on? Well, when you trigger the flowback. When do we trigger it off? Now this one's important. What we want to say here is, in this case, what I did is I'm looking at, well, I don't think I ever had this turn off, but in the spreadsheet, what they said is that the total volume of flowback is 19% of the wellhead capacity. Well, I mean, that's somewhat arbitrary in this model. We could just say, let's just flow all back, but that's what they said in the spreadsheet. So you could change this, and in fact, I should probably put this number 19.3% somewhere, in a data element somewhere in this model. In fact, let me do that right now. I'm surprised I don't have that somewhere. Let me just check. Yeah, I don't. Okay, let me just add that here. So this number is essentially going to cause a trigger to stop the flowback process and allow you to go down and drill another lateral. And it's really just based on what percent of the total amount of injected fluid that went down there, what percent coming back do we want to say, okay, that's enough. I'm not sure if that's always the way that people are deciding when to end the process. Maybe it's just a time factor. Maybe it's based on how much gas they're producing. I have no idea. But we could do that in multiple ways. In fact, we are tracking the amount of gas produced. And if I run the model, let me see what it looks like. Okay, so I probably need to run this for more days to see what on the gas produced. And so let me run this for, let's say, 200 days. Okay, so maybe we get to a point where we say when the flow of the gas produced is getting down to, let's say, 2 cubic meters per day, somewhere down there, maybe we stop the process. So we could say something like that. That's one way to do it. Let's see here. Yeah. Let me think about this. So for us to do that, for us to trigger this based on the gas produced when we stop the flowback, we need to see that we can't just trigger it based on, if I go back up, we can't just trigger this based on this gas produced dropping below 2 because we started out at a value that's below 2, right? So what we want to do is say, has the flowback already started? If it has, then trigger when we are below 2. So let's build that trigger in here, and that will cause us to stop the flowback. Okay, so what we'll do is we'll come back into the well injection folder here, container here, and then go into staging. And then what we'll do is I'll go back to edit mode, and we'll go to the triggering of flowback here. So this triggers the flowback to begin, right? And we want one that will trigger it to end. Just going to move some things around here. Okay, so I think the best way to do this would be with another triggered event here. Okay, we'll call this trigger end flowback. In fact, we may not even need to say trigger there. End the flowback. I'll just be explicit here in the description. Okay, so what we want to say here is that, well, first of all, has the flowback begun? Okay, so the way that you can look at that is you can count the number of times that the triggering has executed. So with any triggered event, you have an output here called event count. So we don't want to end the flowback if this hasn't even started yet. In fact, another way we could do this is we could just make sure that the flowback is on if we're going to end the flowback. So let me just try that real quick. So what I'll do is I'll come in here and I'll say the trigger here is on true when, and I'm going to go back into the model and link to our gas produced right here. And I'll say if that is less than, and we said 2, let me make that a little bit smaller. Let me make it 1 cubic meters per day, something like that. So when that gas produced drops down to that level, let's go ahead and turn off the flowback. Okay, so then we'll come over here and we'll say we're going to trigger it to start on the same trigger we've had. That's good. Now let's go to the trigger off. We'll come here and we'll change this to an event type and say end flowback. But on here, we want to make sure that we account for the fact that the flowback is already running right now. We don't want to trigger this end if it hasn't even started yet. So we'll go here to the more and we'll say check if required condition is true, and I think we need this, yeah. So we need to check to make sure that that itself is on at the moment. I'll try it with and without that. Let's see if that works. Let me see if this triggered. Okay, it did. It triggered on day 35, and the triggering, and so the flowback on off looks like that. Okay, so if I go up to the gas produced level, then you'll see it looks like that. Okay, so I think that looks right. See, we get to about 1 cubic meter per day and it shuts off. Let me just try going back where we were and see what happens if I disable that check if required condition. I think what will happen is it will say it's triggering a true and a false at the same time and give an error. Let's see if it does. Oh, it doesn't. Okay, I guess they didn't trigger at the same time. I was just worried that there would be a chance that it would be triggering on and off at the same time, but I guess it didn't, so that's okay. All right, so now that we have that, now that makes it easy to adjust the timing of when this ends, and we'd probably want to do that, like I said, with the data element. So we'll say trigger flowback. We'll put it in our flowback container here, and we'll just put the data element here and say flowback off trigger. Now let's see. How am I going to describe this? It's triggering, turning off the flowback based on the gas production. I'll have to put that. I'll definitely have to describe this one. And cubic meters per day, and we said 1, but we could change that to 1.5 or something, whatever we want. Now that that's in data, now when we go back to that status element, it's just a matter of referring to that value there that we just created, that variable, which is in flowback. You'll notice I have some red colored text here when I do a link. That's because I'm using versioning. So let me show you what I mean by that. When I build models, I use a version number in the name. So you can see that this model is called Fracking Water LCAV 1.005, and that corresponds exactly, that number, that corresponds to my version number. So when I go here to versioning, then you see that version number is there. And I've just done that manually, the name of my file. I just append that number here every time I make a change. So if I'm coming in here and I say, I want to, add something else, I'll put that in, and then I'll immediately save the model as that new number and then make those changes. But when you are making those changes, you'll see in the browser and any context browser windows that any changes that you make, if you've added elements or edited any elements, you'll see that they've been colored red there. This is nice for when you're working with other people on your model. Okay, so let's see. I need to look at this, what I'm going to be doing next. I don't know at the moment, so let's just not worry about that. Okay, so now that we have that, we know how much gas is produced, the wastewater, we know that, and now we can come over here to the flowback and see how much water is coming back out of the well. That's this flow rate right here. This includes everything that's coming out of the well. And from this, we want to extract out the gas. So there's a fraction there. We use a splitter to separate out the gas. The balance is then what can be recycled. So we have a recycle fraction here. We could say let's recycle 90%, and then we use another splitter for that, and the rest goes to wastewater. So in reality, you'd probably have a pond holding the wastewater and then truck it off or treat it or whatever they're doing there. So then you'd probably want to have another pool element here to have some wastewater pool. The inflows, wastewater. And then you could track how much wastewater goes in there, like that. Okay, so with these splitters, then we can have the recycle then just loop back around into our impoundment, and that's what's going on here. If I double click on this influence line, you can see that we're going from recycle to flowback recycle definition, which is over here in the impoundment, flowback recycle. I can click on it to go there. That shows me this. This is our impoundment here, where we're drawing the water from into the trucks. And this thing is where we're also getting fresh water from the river. And this pool looks like this over time. And what's happening here is that, well, we're done with the injection, right? So that's why the pool just fills up and hits its capacity. We're no longer drawing from it. In reality, what would happen is we're done with one lateral. We would immediately go to the next one and start drilling that one. And so what this model probably should include, if we really want to look at a real system that includes multiple laterals, we would want to build in here in our well injection container, we'd want to build in the ability to put some delay in there for the time it takes to drill another lateral and prep it, perforate and all that stuff, and then begin the whole process over again and draw water out of it. And I think that would then work for one well. Obviously, you'd have multiple wells. So then the question is, do you repeat the process by copying and pasting these containers for each well, or do you make these, vector based? I would say if you have less than 10 total wells, I would say just copy and paste the containers. It's not worth doing vectors for those wells. But if you have more than that, you'd probably want to do the equations as vectors. So So one other thing I wanted to note about the well injection here is that in the staging, if I go into one of these stages, you'll see here that in the well, let me walk through this one more time. Okay, so in stage 1, that's the one furthest down the lateral. The inflow is coming in, that's the injection flow that comes in. Once that fills into there, all I'm going to do is just keep causing that, I'm just going to keep forcing that flow into this first section, but all it does is just spill over into the second pool or the second stage. So I'm not actually saying, okay, fill up the first stage. Once that's full, okay, move over to the next one and fill that one. Okay, move over to the next one. I'm not doing it that way. In GoldSim, you can just have an overflow output on a pool. So I have in here the upper bound. This is the volume per stage. That's that 15. Oh, sorry, it's not 15,000. I said 15,000. It's 1,500 cubic meters. And so what I do is I say once that's filled up, then just keep pushing water in there, but then have it just overflow into the next stage. So it's not exactly the way it works in the field, but it still essentially does the same thing. So this one stops filling essentially because it hits the capacity, but then we overflow into the next one. And so to get the overflow from 1 into 2, in my inflows here, I need to have my overflow from 1 come into this stage 2. And then we just continue that process through each of these. Also, on the outflow side, we have losses. So that's where you inject the fluid up into the fractures and then some of the water is lost. And so what I have there is just some data element that says there's some loss rate, it's a % per day, it's some amount of the total volume of water that's been pushed into there. So in this case, 5% per day of the total amount that's there is lost into the surrounding strata. On the flowback, then we say, okay, if we are in the process of flowing back after everything's filled up, then what I'm going to say is we have a fraction of flowback. That's just this, again, it's just a %. I'm just saying 20% of the total volume that's in excess of the next downstream stage. And like I was saying before, this is really just kind of a rule of thumb that I'm using that's just a way to make sure that we're waiting until the downstream stage. I guess it's actually upstream, depending on which way you're flowing, but that it's just a way to make sure that we wait for the one previous to drain before this one drains. And so that's why I have the this amount minus the next one, so that it just makes sure that we have more water in this stage than the next one. And that's what causes, when I run the model, that's what causes the these lines to not be all along the same path, right? It's because you need the stage ahead to have more water in it than the one downstream before it can drain. It's an approximation. Okay, so I would say this is probably the most complicated part of the whole model. The rest of this whole model is just really managing the flows as they go from one place to the other. But I did have some controls in the impoundment, and so let me go there. On the impoundment side, we have this pool with some water in it, and I'm going to reduce the runtime down back down to 20 days, just so we can see this a little bit better, what's going on. Okay, so you see it has this jagged look to it. What that means is we're controlling the water level in this impoundment based on looking at how much water we can get out of the river into it and how much we're drawing out, but we're using a target water amount and trying to maintain that water amount. And that level that we're trying to maintain is essentially this capacity value right here of 18,000 cubic meters. So this is, another number that's from the spreadsheet. This is how much they have in their impoundment. And what I'm doing is just using a status element. This is very typical for any controls on any kind of pool of water that you're dealing with, right? You definitely want to use a status element. So with the status element, if I open that up, it's called, first of all, it's called pump on, which means this is how much water we're going to be pumping into this this pond. And this pump, by the way, is sitting on the river, right? So we can only get what's available at the diversion. We might not be able to pump everything we want. That's also another important point to make. But what triggers the pump to turn on is that this impoundment is getting kind of low. In our case, it's less than 80% of the capacity. And then we say, okay, go ahead and pump until you're above 90% of capacity. So we're kind of hovering right around that 80-90% is what we should see. And so when you plot the impoundment pool, you should see that we are hovering around that. So the 80% is about right here. We start pumping into it, and the reason we start pumping late is because I built that trigger in the model that says don't start the injection in the well until day 3, if you recall. And so that's why nothing happens until we get here. As soon as we hit this, it says, okay, we're a little below, so let's pump some water in there. We pump it in until we get up to the 90% of the capacity, and then it shuts off. And it stays shut off. That's the good thing about the status element. It stays shut off until we draw down below, did I say 7? I can't remember if it was 75 or 80%. Once it draws down below that point, then we turn the pump back on. And it's not a constant increase here that we're pumping back in to the impoundment, because the pump is on a river that has limited flows available to it. Okay, so we have a little bit of time. The one thing I would like to say is that it would be a really good idea, to put some documentation in here, especially in here, the documentation of how these stages are filled. And so a good way to start that is probably just with a simple diagram. We could put in something like, show the casing, and we could also draw on top of that the strata here, and order, I mean, this all takes time, and I'm not going to do it all, but you can see how you can go through this process. There's that layer and so forth. But then you could just show how, we have these various stages that we go through. I don't know how you would do them. Maybe yeah, I'm not really sure. I think anyway, so you could document, and describe how in each one of these stages, that's what each one of these stages represents here that you're filling up. And then put in some documentation. So that's what that would probably be the next step that I would do before I begin replicating the functionality for multiple laterals. Okay, but since we've decided that we have this this shutoff point that says, okay, we need to shut off the flowback before we begin another injection, then that means we could, in essence, we could say, well, let's trigger a new another injection into another lateral. And so if I were to do that using the same functionality, let's see, currently when we run this, we tell the injection to shut off here, and that's because we filled this up. But obviously this is draining, so it's already drained there, but we don't want to start this back on again until the flowback is stopped over here. That's this one. So let me run this for a longer period and see when that stops. And we probably won't be able to get very far today, but let's see what we can look at here. So we run this, and our flowback stops at day 45. So what we could do is say, let's trigger another injection to turn on when the flowback turns off. But let me plot these two together to see if that's going to cause a problem. Injection on, flowback on. Okay. And I also need to make the green line dashed so I can see what's going on behind it. Okay. So if I said in here, if I put logic in here that says injection turns on again, the red line I mean, that turns on again as soon as the flowback is shut off, I suppose it could work as long as we knew that it was already on before that. We can't just say when the flowback, in the green line, when it's at 0, then turn on the red again because it was at 0 over here. So another thing we could do is say when the flowback ends, when this triggers down here. Let's take a look at that event count. Okay, so what we could say is trigger the injection on again when this thing triggers. So let's try that. Let's see what happens. So if I come over here and say the on trigger, currently it's set at 3 days, but let's add another one that's the end of the flowback. We probably want to delay, right? Because we need to drill the other well or the other lateral. So let's put a delay in here first. So that's in our delays, and it's called an event delay. So we'll come over here and we'll call this trigger new injection. Start injection into new lateral. Okay, so now we trigger that based on our ending of the flowback. End flowback there. And let's say it takes, I don't know, 5 days to drill the next lateral. So that would then trigger our injection on. Okay, so somebody asked, you covered the water flow quite a bit. What about the life cycle part? Yes, and that was my intention, like I mentioned, and I started to go through this and realized very quickly that, and I did actually have a lot of the calculations in here, by the way, for the energy required for pumping all this water, and I realized that it is too much to cover. And I removed a lot of those calculations because this part that I have right here that we're talking about was there is none of this at all in the spreadsheet. All it says in there is there's a total volume. We don't care how long it takes to get any of this out, but we just need to get this total volume out. So, and it's fine for that kind of analysis. And so I guess what's happening here is I'm telling you, this is no longer a life cycle analysis at this point, at this stage that I built this model in. So I'm sorry to disappoint, but my hope is here that this model could be built on. Perhaps I could revisit this in a future webinar. So yeah, that's where it stands. But essentially, it's just the water part. Now, I have a previous version with the energy calculations. I could probably put those back in pretty quick when I post this model, but I didn't want to get way down too much into the detail of that, knowing that there's already a lot right here to bite off. So that's where this is left. But let me see what I can do for you when I post this model, which you will see in probably next week when I get this posted. But anyway, let me just trigger this injection on. I'm sorry, starting a new injection with this new trigger I just built. So I'm going to add and say trigger new injection. Okay, so let's see what happens here. Okay, there. So it started again here, and let's see what happened here with the flowback. Okay, the flowback also started again. Okay, so that looks okay. That's promising. Let's see what these did. Okay, So that also looks okay. Now we have to keep in mind this is not the same lateral, right? So we have one lateral, we do our process here. We have another lateral, we continue that process. Okay, so that all looks fairly promising with just adding that one trigger. And so now when we come back to our impoundment and look at the total volume being drained, okay, so then that's what we see over time. And that makes sense that we've drained, we've been using the water, we don't need it while we have the flow back, and then we need to inject water again into the new lateral, and then we have flow back. So that kind of makes sense right there. And yes, okay, so my plan is now, we're kind of at the end of the presentation. I know this was kind of off, kind of off the cuff a little bit here, but I think it was important for you to see, a little bit of a process of what might happen if you're trying to convert an Excel spreadsheet model to GoldSim. The two different, they can be very different, right? One is static, one is discrete. The spreadsheet, it looks at discrete volumes. It's not necessarily keeping track or using units of measurement like GoldSim would be, and also, and more importantly, time, the time factor, which is critical in here. And I also think it'd be critical in looking at the life cycle, to be honest. And so I think this is a good starting point. I think this would be a better starting point for looking at a life cycle analysis um, than just the lump sum, because I think there would be some things we'd be missing here um, that could be quite critical in looking at total energy used in this model. But you would only know if we built that in. So anyway, that essentially ends the presentation. I hope this was useful. I know I was moving kind of fast, throwing some things together, but I do hope it was useful. And like I said, this is recorded, so you will be able to see this again. And I will be presenting this in the afternoon as well. So, and also be taking time to answer questions. But thanks very much for joining. I hope this was useful. And now I'll stop the recording and then walk through questions.